This is our project, Diagnosing Skin Cancers Using CNNs, and Amanov.
And Diane.
So a little overview of what we're going over, just some background info, then our methodology so far and our current results, and then some future plans we have. So for our background info, what is our project aiming to do? It's basically just diagnosing skin cancer using like machine learning. The first part of our research was to see the images, visualize it, and then pre-process the data. Second part is to visualize the pre-processed data so that to make sure like all the data looks right, which we'll get into later. And our third part of our research is building our model, and then we also have to split the data obviously into like training and testing. And building of the model is like the architecture we use to ensure highest accuracy. And fourth part of research is analyze our accuracy and other metrics. So our objectives currently are to achieve a 90% or higher accuracy for the classification algorithms. Then we also want to see which factors are correlated to each other. For example, we have like various factors like age or something that might affect a person's chance for skin cancer. And then we also want a 90% accuracy for each cancer type. So let's say if I have 100 of one type of cancer, I want 90 of them to be predicted correctly.
So now we'll talk about our research itself. We picked up the HAM 10,000 dataset as it is considered a benchmark dataset for skin cancer classification. All the images are the same size and format, centered close-up images of skin lesion. This reduces the amount of pre-process or data wrangling that we need to do. The metadata also has patient-specific information that is necessary for our project. One of the features of the data was the localization of the cancer. As seen here, a large concentration of the cancer was found in the back and lower extremity. As far as gender, both genders were fairly balanced, so we didn't account for that when we were creating our model. And as per skin cancer types, there was a lot of melanocytic nevi, so we had to augment our data to balance out the data set. And the next slide has some pictures that should be viewed at your own discretion, as they may be disturbing to some audience members. Here are some pictures of melanocytic nevi and melanoma from the HAM 10,000, which are the more common types of cancer in our data set.
Next we'll be talking about like convolutional neural networks and just how they work. So how a convolutional neural network works is that it has a filter, as you can see on the left, that 3 by 3 red grid that passes over the input feature map, which might be like the original input data, which is like an image, or it could be like the features that are learned after some convolutional layers. And what this filter does is it attempts to find different features within the input feature map. So in a first layer, it tends to find like simple features like edges and stuff like that. Then eventually, as you build up on your convolution layers, you attempt to find patterns between the features and correlate those patterns to what you're like the classification you're trying to find. So building our own CNN, right? There are like certain layers we have to look at. One I just talked about is the convolutional layer, which looks at two neighboring. Oh, so the convolutional layer, and then the next is the pooling layer. The pooling layer reduces the spatial size of the input image. There are different types of pooling layer, like max pooling, min pooling, average pooling. Um, then an important layer is the dropout layer, which prevents overfitting by just removing some of the nodes from each layer so that the model doesn't overfit to specific data, which is important for our case because we have a lot of the melanocytic nevi. Then the flatten layers to convert the 2D features into a 1D feature. And this helps in getting the classification into an array of 7, because there are 7 classes of cancer. And the dense layer is you can perform some activation functions on it, and that helps just narrow it down and find the correct classification. So most CNNs directly use JPEG files for the images. However, we decided to take the approach of turning these images into NumPy arrays because it takes less processing power because it's already loaded up and it's easier for the computer to use. Which we noticed which we had some trouble with originally because the computer would crash a lot. But when we converted it and then just saved in a file and loaded up, it was way better. So then what is an array? It's just a list of numbers. So each image is represented in a matrix format, and each pixel, depending on what type of format you're using. So if you're using RGB, there'll be three color channels, R, G, and B. For grayscale, there'll only be one because it only goes from 0 to 255. And it's easier for a computer to analyze trends in numbers than trends in images because there's like a big problem right now with language models trying to understand images rather than just understanding what it's trained on.
So now we'll be discussing our text model. In this section, we will focus on the random forest classifier, which we employ to predict cancer diagnosis based on patient features. Our goal was to train this model to make accurate predictions using the available data. We chose the random forest algorithm for several reasons. It efficiently handles a combination of numerical and categorical data. It is robust to overfitting, which helps ensure that our model performs well on unseen data, and it provides valuable insights into feature importance, allowing us to identify which features are most influential in the prediction process. To achieve this, we followed a series of steps. First, we prepared our training data, consisting of X-train for features and Y-train for the target labels. Next, we initialized the random forest classifier with the necessary parameters. Finally, we trained the model using this data, enabling it to learn patterns and make informed predictions about cancer diagnosis. The training phase begins with using the training data, X-train and Y-train. During this phase, we fit the model to the training data, enabling it to learn patterns and relationships between the features and target labels. A crucial observation during training is that the model starts identifying these patterns and relationships, with a key focus on preventing overfitting, ensuring that the model generalizes well to new unseen data rather than just memorizing the training examples. For evaluation phase, our objective was to assess the model's performance on unseen data to gauge its effectiveness. This involves making predictions on the test set, X test, and then calculating accuracy. Although we initially mentioned using root mean squared, accuracy is typically computed directly by comparing predicted values with actual values to determine the proportion of correct predictions. This evaluation step is vital to understand how well the model performs and how effectively it can predict cancer diagnosis based on new results. In evaluating the performance of our random forest model, we focused on calculating the accuracy score, which provides a measure of how well the model predicts cancer diagnosis. To determine accuracy, we compared the predicted values, denoted as Y-pred, with the actual values, Y-test. The accuracy is computed using the formula accuracy is equal to number of corrected predictions divided by total number of predictions. Our model achieved an accuracy of 70%, indicating that it correctly predicted the diagnosis 70% of the time. This accuracy score reflects the proportion of correctly identified diagnosis relative to the total number of predictions made. While this result demonstrates the model's effectiveness in making accurate predictions, there is room for improvement. Analyzing the performance of our random forest model reveals several strengths and limitations. Strengths include its effective performance with the current dataset, demonstrating the model's ability to handle a diverse range of features. The random forest algorithm's robustness and its capability to manage both numerical and categorical data contributed to its success. However, there are also limitations to consider. The accuracy of the model may vary with different data splits, which can impact consistency in performance. Additionally, there is a potential risk of overfitting or underfitting, which could affect the model's ability to generalize well to new unseen data. To address these limitations and enhance model performance, next steps include conducting feature engineering to refine the input data or incorporating additional data to improve model training. Additionally, hyperparameter tuning can be performed to optimize model settings and potentially boost accuracy.
Next up, we got our multimodal models. So what is multimodality? It's like representation of data using various sources of information. This could be like text data and image data, as it's very common, but it can also, in like a biological standpoint, you could use MRI and X-rays, which are two different datas that carry different information. And what multimodal models try to do is it analyzes various types of data and tries to combine it and improve the accuracy compared to just using one type of data. So this is one of the architectures we used. In the top left, you can see our conv2D, and then we used max pooling layers. Max pooling, it just takes the max value of a pixel out of like a grid of 4 and does that across the whole feature map. Then you just go down, and I explained all those layers before. On the bottom left is the text-based layer. We kept it really simple because we wanted it to just run quickly for our first few rounds rather than um, wasting a lot of time on processing power. And um, on the right is when you combine the image and text data, and then you can run your normal model on it and get that output of 7 on the bottom, as you can see in the dense. The accuracy this model got was 66.42%, which isn't great, and we hope to improve that, as we can see in our next model, which is a very similar architecture, but slightly more nodes and one more layer. And this model got an accuracy of 71.48, which is an improvement, but it needs to be improved quite a bit for that 90 plus.
And now
Um,
we'll discuss some of the challenges we faced. To enhance our model's performance and prevent overfitting, we implemented data normalization techniques. This involved artificially creating or removing images to ensure our model trained on a diverse and representative dataset. Initially, we leveraged the ASDRP server cluster to run our models using Keras and TensorFlow, which provided substantial computational resources. However, for greater flexibility and efficiency, we later transitioned to running the model locally on VS Code. This shift allowed us to streamline our workflow and better manage our experiments. Additionally, we standardized our NumPy arrays into tensors, which was a crucial step to ensure compatibility with TensorFlow's accuracy functions. This standardization allowed us to effectively compute and evaluate the model's accuracy, facilitating more precise performance assessments.
Next up are future ideas, which is like a major part right now. We got data augmentation down using image data generator, which basically performs simple variations on the current images. And as you can see, the melanocytic nevi is no longer just standing alone. All the other types of cancers are also equalized with it, so the model is not biased to just NV. How this works is each image is like rotated, flipped, some transformation is performed on it, simple calculations like that. But what's important is that we also need to maintain the text data, especially for the multimodal. So we had to run the image data generator like we had to check for what class of cancer it was and then run the image data generator and replicate the text data frame row. But we still have to train the model on this data augmentation. So that will be our next step. Then our second goal is to tune all the models to get above 95% accuracy. Right now we're still just going for 90, but we really hope for that 95 plus. And thank you. Any questions?